Imagine rain so acidic it could strip paint off your car. In the 1980s, that wasn't imagination, that was Tuesday in places like the Adirondack Mountains. Over 200 lakes became so acidic they turned crystal clear because nothing could survive in them. The pH dropped to around 3.7, about the same acidity as soda. Statues that had stood for centuries dissolved like sugar cubes. Scientists warned we were witnessing an environmental apocalypse in slow motion. Then governments listened, and the greatest environmental recovery you've never heard about unfolded. But here's the strange part, we completely forgot it happened. The forgotten environmental apocalypse. Here's the thing about environmental disasters, we remember the ones we didn't solve. Chernobyl still haunts us. The ozone hole occupied headlines for decades. But acid rain, the environmental crisis that had scientists predicting the death of entire forests and the sterilization of thousands of lakes, just disappeared from our collective memory. One day it was everywhere, the next day it was nowhere. Which is strange because for about 2 decades, acid rain was the environmental boogeyman that kept everyone awake at night. Picture this, it's 1985 and you're driving through the Adirondack Mountains in upstate New York. What you see looks like something out of a post-apocalyptic movie. Entire mountainsides stripped bare of leaves, their skeletal branches reaching toward gray skies like the arms of the dying. Trees that had stood for decades now reduced to bleached wooden tombstones. The forest floor, normally thick with undergrowth and buzzing with life, sits empty and silent. This wasn't the result of a fire or a plague of insects. This was the work of rain. The lakes told an even more disturbing story. In the 1980s, more than 200 lakes in the Adirondacks had become so acidic that they could no longer support fish. These weren't small ponds either. We're talking about bodies of water that had sustained ecosystems for thousands of years, now rendered lifeless by precipitation with a pH lower than orange juice. The water looked pristine, clearer than it had ever been because there was nothing left alive in it to cloud the view. Local fishing guides watched their livelihoods evaporate as anglers stopped coming to fish in dead lakes. The destruction wasn't limited to remote wilderness areas. Ancient limestone buildings and monuments that had survived wars, natural disasters, and centuries of weathering began dissolving at an alarming rate. The Statue of Liberty's copper skin turned green faster than expected. Gothic cathedrals across Europe watched their intricate stone carvings melt away like ice sculptures in summer heat. In Athens, the Parthenon suffered more damage from acid rain in the 20th century than it had in the previous 2,000 years combined. But the real horror show was happening in Germany's Black Forest, where entire stands of spruce trees were dying from the top down. German scientists coined a term for it, Waldsterben or forest death. By the mid-1980s, more than half of Germany's forests showed signs of damage, with sites like the Black Triangle seeing over 50% of trees affected according to Swedish Environmental Agency reports. The phenomenon spread across Central Europe like a slow-motion plague, with similar devastation occurring across multiple continents as forests collapsed under their own weakened weight. The international blame game that followed was unlike anything the environmental movement had seen before. But here's where things get interesting. Back in 1977, the OECD had published what they called a blame matrix, research showing that sulfur compounds could travel hundreds of miles through the atmosphere before falling as acid rain. This was a pivotal moment when policymakers first realized that pollution didn't respect borders. Countries pointed fingers across borders with the fury usually reserved for trade disputes or territorial conflicts. Canada accused the United States of poisoning its lakes with sulfur dioxide from Midwest power plants. The Scandinavian countries filed formal complaints against Britain, claiming that British coal plants were killing Norwegian forests and Swedish fish populations. The situation became so tense that acid rain featured in high-level diplomatic meetings between world leaders. For anyone who lived through the 1980s, acid rain was unavoidable. It dominated news cycles with the same persistence that climate change does today. Time magazine ran cover stories with headlines like "The Poisoning of America." Television specials showed dramatic footage of dead forests and empty lakes. Environmental groups organized rallies where protesters held signs reading "Stop Acid Rain Now" and wore gas masks to dramatize the invisible threat falling from the sky. The predictions grew increasingly apocalyptic as scientists gathered more data. Researchers warned that if current emission trends continued, entire regions of North America and Europe would become ecological wastelands within decades. Some studies suggested that acid rain could make large areas of the northeastern United States uninhabitable for most plant and animal life. Computer models projected the collapse of forest ecosystems across multiple continents. The scientific community spoke with unusual unanimity about the scale and urgency of the threat. What made acid rain particularly terrifying was its insidious nature. Unlike oil spills or toxic waste dumps which caused immediate and visible damage, acid rain worked slowly and quietly. A forest might look healthy one year and show signs of distress the next, with no obvious cause visible to the naked eye. The invisible killer fell from clouds that looked perfectly normal. Children played in rain that was slowly poisoning the environment around them. The media coverage reached fever pitch when scientists began connecting acid rain to human health problems. Studies suggested that the same atmospheric chemistry creating acid rain was producing fine particulates that could damage lungs and worsen respiratory conditions. Suddenly, acid rain wasn't just killing trees and fish, it was potentially killing people. The threat seemed to lurk everywhere, falling silently from the sky onto schools, playgrounds, and neighborhoods. Environmental scientists found themselves in the unfamiliar position of being taken seriously by governments and the general public. Congressional hearings featured dramatic testimony about dying ecosystems. European parliaments debated emergency measures to address transboundary pollution. Research funding flowed to laboratories studying atmospheric chemistry and ecosystem damage. For once, the scientific community's warnings about environmental destruction were met with genuine alarm rather than skeptical dismissal. The crisis mentality reached its peak in the mid-1980s when several high-profile studies confirmed the worst fears about acid rain's environmental impact. The National Acid Precipitation Assessment Program, a massive 10-year research effort involving multiple government agencies, documented extensive damage to forests, lakes, and streams across the eastern United States. Similar studies in Europe painted an equally grim picture of ecosystem collapse across the continent. Yet here's what makes the acid rain story so remarkable. The scientists were absolutely right. This wasn't environmental hysteria or media sensationalism blown out of proportion. The chemistry was sound, the damage was real, and the threat was genuine. Lakes really were dying, forests really were collapsing, ancient monuments really were dissolving faster than ever before in recorded history. The apocalyptic predictions weren't based on wild speculation. They were grounded in solid research and careful observation. The irony is almost too perfect. At a time when environmental scientists are often dismissed as alarmists or accused of exaggerating threats for political gain, acid rain represents a case where they got it exactly right. They identified a massive environmental problem, traced its causes with scientific precision, predicted its consequences with remarkable accuracy, and even proposed realistic solutions. And unlike so many environmental issues that drag on for decades with endless debate about causes and solutions, acid rain had a clear villain, measurable impacts, and obvious remedies. What happened next would prove that sometimes, just sometimes, human beings can actually solve the environmental problems they create. But first, the world had to accept that the scientists weren't crying wolf. The dead forests and lifeless lakes provided all the evidence anyone needed that this particular environmental apocalypse was very real indeed. When scientists actually got it right. The breakthrough that changed everything came on July 24, 1963, when Gene Likens and his research team were conducting routine water quality measurements at the Hubbard Brook Experimental Forest in New Hampshire. They expected to find rainwater with a pH around 5.6, which is what you get when water naturally reacts with carbon dioxide in the atmosphere. Instead, their instruments showed a reading of 3.7, nearly 100 times more acidic than expected and roughly the same acidity as orange juice. The team ran the test multiple times, convinced their equipment was malfunctioning. It wasn't. What made this discovery so powerful was that it happened at exactly the right place and time. The Hubbard Brook site had been established specifically to study long-term ecosystem health, complete with sophisticated monitoring equipment and detailed measurement protocols. This wasn't some random observation by a graduate student taking water samples for a class project. The research station had the infrastructure and credibility to document something extraordinary, and more importantly, to prove that it wasn't a fluke. Likens and his colleague Herbert Borman realized they had stumbled onto something much bigger than contaminated rainwater in one New Hampshire forest. They began expanding their measurements across the northeastern United States, collecting precipitation samples from dozens of sites. The results painted a disturbing picture. The acidic rain wasn't limited to areas near obvious pollution sources. Remote wilderness areas hundreds of miles from the nearest factory or power plant were receiving precipitation with pH levels that would make your dentist cringe. The eureka moment came when the researchers started mapping their data. The pattern became unmistakable. The most acidic precipitation was occurring downwind of major industrial centers in the Midwest. Sulfur dioxide and nitrogen oxides were being pumped out of smokestacks in Ohio and Pennsylvania, then carried by prevailing winds to fall as acid rain on forests and lakes in New York, Vermont, and New Hampshire. For the first time, scientists had connected specific industrial emissions to environmental damage occurring hundreds of miles away. In 1974, Likens and Borman published their findings in the journal Science with a paper titled Acid Rain, a Serious Environmental Problem. The timing couldn't have been better. The environmental movement was gaining momentum following the first Earth Day in 1970, and the public was primed to hear about new ecological threats. But more importantly, The scientific community was ready to take their colleagues seriously when they presented hard data about atmospheric chemistry and ecosystem damage. The research methodology was bulletproof in ways that environmental science rarely achieves. The Hubbard Brook team had established baseline measurements before the problem became severe, so they could document exactly how conditions had changed over time. They could trace the chemical pathway from industrial smokestacks to dying fish in Adirondack lakes. They had controlled experiments, long-term data sets, and reproducible results. When critics tried to poke holes in their conclusions, the scientists had answers backed by decades of meticulous measurements. The experimental work conducted at Ontario's Experimental Lakes area provided the smoking gun that sealed the case. Researcher David Skindler and his team did something that would make any environmental lawyer salivate. They conducted a controlled experiment that proved causation, not just correlation. By acidifying one lake, they proved fish died of starvation because acid dissolved their prey's shells. Within a few years, a thriving aquatic ecosystem had been reduced to a biological desert. The beauty of the acid rain research was its clarity. Unlike climate change, which involves complex feedback loops and century-long timescales, acid rain had a simple cause-and-effect relationship that anyone could understand. Burning fossil fuels releases sulfur dioxide. Sulfur dioxide reacts with water in the atmosphere to form sulfuric acid. Sulfuric acid falls as precipitation and kills stuff. The chemistry was straightforward, the impacts were measurable, and the timeline was immediate enough that researchers could document changes within a few years rather than decades. This simplicity made acid rain research almost immune to the usual tactics that industries use to muddy environmental science. The Edison Electric Institute, representing coal-fired power plants, tried their best to fund counterstudies and create doubt about the findings. But when lakes are literally dying and you can measure the exact pH of the rain falling into them, it's hard to convince anyone that the problem might be caused by solar flares or natural climate cycles. The cause and effect relationship was too obvious and too well documented to dispute convincingly. The scientific community rallied around the acid rain research with unusual unanimity. Atmospheric chemists confirmed the chemical pathways. Ecologists documented the biological impacts. Geologists showed how acid rain was accelerating the weathering of stone monuments and buildings. By the early 1980s, hundreds of peer-reviewed studies from multiple disciplines had confirmed the basic conclusions. Industrial emissions were creating acid rain, and acid rain was causing widespread environmental damage. What made the scientific response even more remarkable was how quickly researchers developed sophisticated tools to study the problem. The regional acid deposition model allowed scientists to predict where acid rain would fall based on emission sources and weather patterns, something no atmospheric model had accomplished before. Atmospheric monitoring networks tracked pollution as it moved across state and national boundaries. Ecosystem studies documented recovery rates for damaged forests and lakes. Within 2 decades, the scientific community had built a comprehensive understanding of every aspect of the acid rain problem. The breakthrough research created something almost unheard of in environmental science, a clear problem with an obvious solution. Scientists could point to specific smokestacks and say, install scrubbers on those and the problem goes away. They could model exactly how much emission reductions would be needed to restore ecosystem health. They could predict recovery timelines for damaged lakes and forests. Environmental problems are usually messy, complicated, and politically ambiguous. Acid rain was refreshingly straightforward. Perhaps most importantly, the scientists got their timing right. They identified the problem before it became irreversible, documented the damage while it was still occurring, and proposed solutions while there was still time to implement them. They didn't wait for perfect data or complete understanding before sounding the alarm. They saw a clear threat to major ecosystems and spoke up loudly enough to get everyone's attention. The result was a rare moment in environmental history when scientists made accurate predictions about ecological disaster and were actually taken seriously by the people who could do something about it. The research was solid, the threat was real, and the solutions were achievable. For once, environmental scientists found themselves in the unfamiliar position of being both right and heard. But here's where the story gets really interesting. The solution that saved entire ecosystems turned out to be surprisingly mundane. The most boring solution that actually worked. You want to know the really strange thing about solving acid rain? The technology that saved entire ecosystems wasn't some breakthrough invention or revolutionary green energy system. It wasn't solar panels or wind turbines or anything that would make for good photo ops at environmental rallies. The solution was so mundane, so industrial, and so thoroughly unsexy that most people never even noticed it was happening. We're talking about the environmental equivalent of fixing a global crisis with really good air filters. The hero of this story is something called a sulfur scrubber, which sounds about as exciting as it actually is. Picture a massive tower attached to a coal power plant filled with what amounts to a glorified car wash for smokestack exhaust. The process works like this. Scrubbers spray smokestack gases with limestone water, transforming sulfur dioxide into harmless gypsum. Instead of sulfur dioxide shooting out of the smokestack and eventually becoming acid rain, you get a wet paste that can be turned into wallboard for construction projects. The engineering behind scrubbers is so straightforward that it almost feels anticlimactic. Take polluted air, spray it with lime water, collect the sludge, and voila, no more acid rain precursors floating around the atmosphere. The technology existed in various forms since the 1930s, but it took decades for anyone to mandate its widespread use. The EPA's acid rain program created competition among different pollution control technologies, spurring improvements and innovations that drove down costs and increased effectiveness. Modern scrubbers remove over 95% of sulfur dioxide emissions, proving their remarkable effectiveness at industrial scale. The automobile industry contributed its own brand of boring but effective technology through catalytic converters. These devices look like metallic honeycomb structures stuffed into your car's exhaust system. Exhaust gases flow through chambers lined with platinum, palladium, and rhodium, which act as catalysts to break down nitrogen oxides and other pollutants into less harmful compounds. The chemistry happens at temperatures hot enough to melt copper, transforming molecules that would otherwise contribute to acid rain into nitrogen, oxygen, and water vapor. By 2000, every new U.S. car had one, cutting nitrogen oxide pollution by over 90%. What made catalytic converters particularly effective was their universality. Every new car sold in the United States after 1975 was required to have one, which meant that within a couple of decades, the entire fleet of American automobiles was equipped with pollution control technology. Unlike voluntary programs or incentive-based systems, this was a straightforward regulatory mandate that left no room for interpretation. Car manufacturers complained about the costs, but they had no choice but to comply. The fuel processing side of the equation involved equally unspectacular improvements to refinery operations. Coal washing became standard practice at many facilities, removing sulfur compounds before the coal ever reached a power plant. Petroleum refineries invested in hydrotreating units that stripped sulfur from gasoline and diesel fuel using hydrogen gas at high temperatures and pressures. The result was cleaner-burning fuel that produced fewer acid rain precursors when combusted. These technologies shared a common characteristic that made them politically feasible. They were invisible to consumers. People didn't have to change their driving habits, switch to different energy sources, or make any lifestyle adjustments whatsoever. The pollution controls worked behind the scenes, embedded in industrial processes that most citizens never thought about. Power companies installed scrubbers, automakers added catalytic converters, and refineries upgraded their equipment, all while ordinary people went about their daily lives completely unaware that an environmental revolution was happening in their exhaust pipes and electrical grid. The implementation happened with remarkable speed once the regulatory framework was in place. The Clean Air Act amendments of 1990 created a cap-and-trade system for sulfur dioxide emissions that gave power companies flexibility in how they reduced pollution while setting firm limits on total emissions. Some utilities chose to install scrubbers, others switched to lower sulfur coal, and many did both. The market-based approach allowed companies to find the most cost-effective solutions, while ensuring that overall emissions declined year after year. The success of these unglamorous solutions highlights something important about environmental problem-solving. The most effective interventions often happen at the source of pollution rather than trying to change human behavior downstream. Instead of asking millions of people to drive less or use less electricity, acid rain mitigation focused on making the cars and power plants cleaner. This approach avoided the usual political battles over lifestyle changes and economic sacrifice that derail so many environmental initiatives. The contrast with other environmental challenges is striking. Climate change advocates promote everything from electric vehicles to plant-based diets to carbon taxes, all of which require significant changes in how people live and work. Ozone depletion was addressed by banning specific chemicals and finding substitutes, which created some economic disruption but didn't require consumer behavior changes. Acid rain was solved with technology that made existing systems cleaner, without requiring anyone to use them differently. The boring nature of the solution probably contributed to how quickly the public forgot about acid rain as an issue. There were no dramatic announcements about revolutionary breakthroughs, no ribbon-cutting ceremonies for scrubber installations, and no consumer products marketed as acid rain solutions. The technology worked quietly and efficiently, removing pollutants from the air without fanfare or publicity. Success looked like the absence of news rather than the presence of dramatic improvements. Industrial solutions also had the advantage of being scalable and permanent once implemented. A single scrubber installation could eliminate more sulfur dioxide emissions than thousands of individual behavior changes, and it would continue operating for decades with routine maintenance. The technology didn't depend on sustained public interest or political support beyond the initial regulatory requirements. Once the equipment was installed and operating, it would keep working regardless of whether anyone remembered why it was there. The lesson from acid rain is almost disappointingly simple. When you have a pollution problem, the most straightforward solution is often to install better pollution controls. No protests required, no lifestyle changes needed, just better engineering applied at the right scale. It's the kind of boring success story that environmental movements should probably celebrate more often, even if it doesn't make for compelling social media content. But of course, having the right technology is only half the battle. Someone still had to make the political decision to actually use it. The policy miracle nobody remembers. The Clean Air Act amendments of 1990 represented something that almost never happens in environmental politics. When faced with a massive ecological crisis, governments actually worked together, moved quickly, and implemented solutions that worked better than anyone expected. If you're looking for evidence that international cooperation on environmental issues is possible, acid rain represents the closest thing to a miracle we're likely to see in our lifetimes. The legislative breakthrough wasn't just ambitious in scope or goals. What made this law remarkable was that politicians actually designed a system that worked. The amendments created the acid rain program, which established a permanent cap on sulfur dioxide emissions from power plants across the country. This wasn't some voluntary agreement or aspirational target that companies could ignore when it became inconvenient. It was a hard limit with real enforcement mechanisms and serious penalties for violations. The genius of the 1990 amendments lay in their use of market-based mechanisms rather than traditional command and control regulations. Instead of telling every power plant exactly what technology to install or which fuels to burn, the law created a cap-and-trade system that let companies figure out the most cost-effective ways to reduce their emissions. Utilities could buy and sell emission allowances, bank them for future use, or invest in pollution controls that reduced their need for allowances altogether. The system gave companies flexibility while guaranteeing that total emissions would decline year after year. This approach proved politically palatable because it recognized that different companies face different costs for reducing pollution. A utility with older, dirtier power plants might find it cheaper to buy allowances from a company that had already invested in clean technology. Meanwhile, the company with cleaner plants could sell its excess allowances and use the revenue to fund additional improvements. The result was a competitive market for pollution reduction that achieved environmental goals at a fraction of the cost that traditional regulations would have required. The political maneuvering required to pass these amendments involved legislative horse trading that would make seasoned diplomats proud. Environmental groups had to accept market-based solutions instead of their preferred approach of shutting down coal plants entirely. The coal industry had to accept mandatory emission reductions instead of their preferred approach of doing nothing and hoping the problem would go away. Electric utilities had to accept caps on their emissions, but gained flexibility in how to meet those limits. President George H.W. Bush deserves credit for making acid rain reduction a priority despite opposition from within his own party. Bush had campaigned on environmental issues and saw acid rain as an opportunity to demonstrate that Republicans could address environmental problems without destroying the economy. His administration worked closely with Congress to design a system that could attract bipartisan support, which in retrospect seems like something from an alternate universe, where politicians actually solve problems instead of just arguing about them. The international dimension of acid rain policy created diplomatic challenges that make current climate negotiations look simple by comparison. The problem was fundamentally transboundary, with pollution from power plants in the American Midwest killing fish in Canadian lakes and European emissions destroying Scandinavian forests. Countries had to overcome the basic prisoner's dilemma of environmental cooperation. Why should we reduce our emissions if our neighbors might not reduce theirs? The breakthrough in international cooperation came with the 1979 Convention on Long-Range Transboundary Air Pollution, which brought together 32 European countries plus the United States and Canada to address cross-border air pollution. This treaty established the framework for scientific cooperation and information sharing that would prove essential for developing effective policies. The convention grew over time to include more than 51 member countries, and expanded its scope to cover additional pollutants beyond the original focus on acid rain precursors. The US-Canada Air Quality Agreement of 1991 represented the kind of international environmental cooperation that diplomats dream about but rarely achieve. Both countries committed to specific emission reduction targets and established monitoring systems to track progress toward those goals. The agreement included enforcement mechanisms and regular review processes to ensure that both sides lived up to their commitments. Canadian officials had been pressing for action on acid rain for years, and the agreement gave them the tools they needed to hold American power companies accountable for pollution that was killing Canadian ecosystems. European cooperation on acid rain involved even more complex negotiations because the pollution crossed multiple national boundaries. A coal plant in Britain could contribute to acid rain in Norway, while emissions from Germany affected forests in the Czech Republic. The European approach relied heavily on scientific research and monitoring to establish clear cause-and-effect relationships between emission sources and environmental damage. This evidence-based approach made it harder for countries to deny responsibility for transboundary pollution. The speed of the policy response was unprecedented in environmental politics. From the initial scientific discoveries in the 1960s to comprehensive international agreements in the 1990s, the timeline for acid rain policy was measured in decades rather than the centuries that characterize most environmental issues. Climate change negotiations have been ongoing for more than 30 years with limited success. Biodiversity loss has been recognized as a major problem for decades with minimal policy response. Acid rain went from scientific curiosity to international treaty obligations in roughly the same time it took to build the interstate highway system. Industry resistance to acid rain regulations followed the predictable playbook of questioning the science, exaggerating the costs, and predicting economic disaster. The Edison Electric Institute, representing electric utilities, funded studies designed to cast doubt on the connection between power plant emissions and ecosystem damage. Coal companies warned that emission controls would destroy mining jobs and increase electricity prices. Auto manufacturers complained that catalytic converters would make cars more expensive and less reliable. What made the acid rain case different was that these industry arguments ultimately failed to prevent policy action. The scientific evidence was too strong, the environmental damage was too visible, and the public pressure was too intense for politicians to ignore. Industry groups found themselves negotiating the details of emission controls rather than fighting the basic principle that something needed to be done about acid rain. The economic arguments against acid rain controls proved to be vastly overstated, just as they are for most environmental regulations. The cap-and-trade system for sulfur dioxide emissions cost far less than industry estimates predicted. Technological innovation drove down the price of pollution controls faster than anyone expected. The market-based approach gave companies incentives to find creative solutions that minimized costs while maximizing emission reductions. The policy success extended beyond national borders as other countries adopted similar approaches to acid rain control. The European Union implemented its own emission trading systems. Individual countries upgraded their environmental regulations to address acid rain precursors. International organizations provided technical assistance to developing countries that wanted to avoid the environmental mistakes that had plagued industrialized nations. But here's the thing about policy victories: they're only as impressive as the results they produce. And when it comes to measuring the actual impact of all this legislative maneuvering and international cooperation, the numbers tell a story that's almost too good to believe. The numbers that prove miracles happen. Sometimes the most remarkable thing about solving a massive environmental crisis is just how spectacularly successful the solution can be. We're talking about numbers so dramatic that they sound like someone made them up to win an argument at a dinner party. But these statistics are real, they're documented, and they represent one of the most thorough environmental turnarounds in recorded history. Let's start with the headline figure that should make every environmental scientist weep tears of joy. Sulfur dioxide emissions in the United States dropped by 94% between 1970 and 2023. That's not a typo. We're talking about a 94% reduction in the primary chemical responsible for acid rain, achieved over the span of about 5 decades. To put that in perspective, annual sulfur dioxide emissions fell from roughly 28 million tons in 1970 to just 1.7 million tons in 2023. If environmental victories had victory laps, this one would circle the globe several times. The acid rain program alone, which kicked into high gear in 1995, has been responsible for staggering reductions in pollution from power plants. From 1990 to 2023, sources covered by acid rain regulations reduced their sulfur dioxide emissions by 15.1 million tons. That represents a 96% decrease from 1990 levels. For context, that's roughly equivalent to taking every coal plant in the entire southeastern United States offline, except we didn't shut down the plants. We just made them clean enough that their emissions became negligible. The emission rate improvements tell an even more impressive story. The average sulfur dioxide emission rate for power plants covered by acid rain programs fell to 0.06 pounds per million British thermal units in 2023. This represents a 92% reduction from 2005 rates, with most of these improvements coming from coal-fired power plants that historically were the worst offenders. Coal plants are still operating, still generating electricity, but they're doing it while producing a fraction of the pollution they used to create. Nitrogen oxides, the other major contributor to acid rain, saw similarly dramatic reductions. Annual emissions from power plants dropped by 5.8 million tons between 1990 and 2023, representing a 90% reduction. The average nitrogen oxide emission rate fell by 77% from 2005 to 2023. These improvements happened while electricity generation remained relatively stable, proving that environmental protection and economic activity can coexist when the right policies are in place. Broader air quality improvements paint an even more remarkable picture of environmental recovery. Since 1970, the United States has reduced aggregate emissions of the 6 criteria air pollutants by 78%. During the same period, the gross domestic product grew by 321%, vehicle miles traveled increased by 194%, population grew by 63%, and energy consumption rose by 42%. The economy expanded dramatically while pollution plummeted, demolishing the argument that environmental protection requires economic sacrifice. Regional success stories showcase just how thoroughly acid rain has been conquered in many areas. From 2000 to 2023, states participating in air quality improvement programs achieved a 44% decrease in combined emissions of major pollutants while experiencing an 84% increase in gross domestic product and a 30% increase in population. Economic growth and environmental improvement occurred simultaneously, creating the kind of win-win scenario that policymakers dream about but rarely achieve. The ecosystem recovery stories are where the statistics become genuinely inspiring. Lakes that were declared biologically dead in the 1980s now support thriving fish populations. The Adirondack Park, which had more than 200 acidified lakes at the height of the crisis, has seen dramatic improvements in water chemistry. Lake pH levels have risen steadily as acid rain inputs declined, allowing aquatic ecosystems to rebuild from the ground up. Fish species that disappeared entirely from some lakes have been successfully reintroduced and are now sustaining healthy populations. Forest recovery has been equally impressive in many regions. The German forests that were dying from acid rain in the 1980s have largely recovered, with new tree growth replacing the skeletal remains of acid-damaged stands. Soil chemistry has improved as acidic inputs declined, allowing forests to rebuild the nutrient base that supports healthy tree growth. Sugar maple populations in northeastern forests, which were severely stressed by acid rain, have shown remarkable recovery as precipitation pH has returned to more natural levels. The monument preservation success stories provide some of the most visible evidence of acid rain recovery. Ancient stone structures that were dissolving at alarming rates in the 1980s have seen their deterioration slow dramatically as atmospheric acidity declined. The Lincoln Memorial in Washington, D.C., which was showing significant acid damage in the 1980s, now faces much lower rates of stone weathering thanks to cleaner air. European cathedrals and historic buildings have experienced similar improvements in preservation rates. Air quality monitoring data shows consistent improvements across multiple pollutants since implementation of acid rain controls. Ambient concentrations of sulfur dioxide, nitrogen dioxide, carbon monoxide, lead, and ozone have all declined by at least 26% since 1980. Fine particulate matter concentrations have dropped by at least 29% since 2000, contributing to improved visibility and public health outcomes in previously polluted regions. The speed of environmental recovery has surprised even optimistic scientists. Lakes that were expected to take decades to recover have shown improvement within years of reduced acid inputs. Forest soils that accumulated decades of acidic deposits have begun neutralizing faster than predicted. The resilience of natural ecosystems, once given the chance to recover, has exceeded the most hopeful projections from the early days of acid rain research. Perhaps the most remarkable aspect of these statistics is how thoroughly they represent success that nobody talks about anymore. We solved acid rain so completely that it disappeared from public consciousness. Environmental groups moved on to other issues. Politicians stopped mentioning it in speeches. News organizations stopped covering it because there was no crisis left to report. The contrast with other environmental challenges is striking. Climate change discussions focus on targets and goals and aspirational objectives. Biodiversity conservation efforts struggle to show measurable progress. Ocean acidification research documents ongoing deterioration. Acid rain stands alone as an environmental problem where the statistics tell a story of complete victory rather than incremental progress or continued decline. These numbers represent something genuinely unprecedented in environmental history. We identified a major ecological threat, developed effective solutions, implemented them at scale, and achieved results that exceeded our most optimistic projections. The statistics prove that environmental problems can be solved completely, not just managed or minimized. But there's something important about this success story that makes it incomplete. Where acid rain never got the memo, the success in wealthy nations stands in stark contrast to what's happening elsewhere around the globe. While we were celebrating our acid rain victory in North America and Europe, other parts of the world were just getting started with their own acid rain crisis. Right now, in 2025, there are regions experiencing the same kind of environmental devastation that terrified scientists in the 1980s. The dead lakes, the dying forests, the dissolving monuments, it's all happening again, just in different places. India currently holds the dubious distinction of leading the world in sulfur dioxide emissions, making it ground zero for contemporary acid rain problems. The country's rapid industrialization has created exactly the same conditions that plagued the American Midwest in the 1970s: coal-fired power plants burning high-sulfur fuel without adequate emission controls. Indian cities regularly experience precipitation with pH levels that would have made headlines in 1980s America. The environmental damage follows the same predictable pattern that scientists documented decades ago, but now it's happening to ecosystems that have never experienced industrial-scale acid deposition. The Indian government recognized the problem and mandated that industrial operations install sulfur scrubbers on their power plants. The original deadline was set for 2017, which seemed reasonable given that the technology had been perfected decades earlier. But implementation proved more challenging than policymakers anticipated. The deadline got pushed back to 2026, and even that timeline looks optimistic given the slow pace of compliance. Meanwhile, acid rain continues falling on Indian forests, lakes, and agricultural regions that lack the resources to monitor or document the damage being done to their ecosystems. China presents a more complex case study in acid rain management. The country experienced massive acid rain problems during its period of rapid industrialization, with more than 30% of Chinese territory affected by acidic precipitation in the 1990s. Chinese scientists documented the same kinds of ecosystem damage that had occurred in North America and Europe: lakes becoming too acidic to support fish, forests showing signs of stress from acidic soils, and urban air quality deteriorating to dangerous levels. But China also demonstrates that developing countries can address acid rain when they commit resources to the problem. The Chinese government implemented pollution control zones that limited sulfur dioxide emissions from industrial sources. These controls worked remarkably well, reducing the percentage of the country affected by acid rain from over 30% to about 5% by 2018. The improvement represents one of the fastest large-scale environmental recoveries in modern history, proving that acid rain solutions can be implemented quickly when governments prioritize the issue. However, Chinese environmental officials are now warning about a new threat that could undermine these gains. Nitrogen oxide emissions appear to be rising, potentially creating a second wave of acid rain problems. This highlights something important about acid rain chemistry. You need to control multiple pollutants simultaneously to prevent the problem from simply shifting from one chemical pathway to another. Brazil represents an emerging acid rain concern that highlights how the problem can spread to unexpected places. Rio de Janeiro and other industrial regions are now experiencing acidic precipitation that affects both urban and rural areas. Brazilian scientists are documenting the same kinds of environmental impacts that characterized acid rain elsewhere: damage to building materials, stress on forest ecosystems, and degradation of water quality in lakes and rivers. West Africa is seeing similar trends as countries in the region develop their industrial capacity without learning from the environmental mistakes of earlier industrializers. Coal-fired power plants and heavy industry are creating the same atmospheric chemistry that produced acid rain elsewhere, but without the emission controls that prevent environmental damage. The result is predictable. Ecosystems that evolved without exposure to industrial pollution are now experiencing rapid acidification, with consequences that scientists are only beginning to document. The global inequality in environmental solutions becomes starkly apparent when you compare acid rain conditions across different regions. North American and European power plants are equipped with sophisticated scrubbers that remove more than 95% of sulfur dioxide emissions. Meanwhile, power plants in developing countries often operate without any emission controls whatsoever, creating pollution levels that would have been illegal in industrialized countries for decades. This technological disparity reflects broader patterns in global environmental policy. Developing countries often lack the regulatory infrastructure to mandate emission controls, the financial resources to subsidize pollution control equipment, or the technical expertise to maintain sophisticated environmental technologies. International development assistance programs sometimes provide funding for basic infrastructure like roads and hospitals, but rarely prioritize environmental protection measures that would prevent acid rain before it becomes a crisis. The knowledge gap is smaller than the implementation gap. Scientists in countries experiencing acid rain problems understand the chemistry, recognize the environmental impacts, and know what technologies would solve the problem. The research on acid rain mitigation has been published in international journals, presented at scientific conferences, and incorporated into environmental textbooks used around the world. The information is available, but translating knowledge into effective policy and technological implementation remains challenging. The economic arguments that delayed acid rain controls in industrialized countries are being repeated in developing regions today. Power companies argue that emission controls will increase electricity costs and reduce competitiveness. Government officials worry that environmental regulations will slow industrial development and economic growth. These concerns are not entirely unfounded, but they ignore the long-term costs of environmental damage and the health impacts of air pollution on local populations. The technology transfer mechanisms that could spread acid rain solutions globally exist, but operate slowly and inefficiently. International development banks sometimes fund environmental projects that include emission controls, but these represent a small fraction of total industrial development. Private companies that manufacture pollution control equipment have economic incentives to sell their products globally, but they face barriers related to financing, local regulations, and technical support requirements. The acid rain situation in developing countries reveals something troubling about global environmental progress. We have the technology to prevent acid rain everywhere, we understand the science completely, and we have proven policy frameworks that work effectively. Yet the problem persists and spreads because environmental solutions remain unevenly distributed across the global economy. Meanwhile, in the countries that actually solved the problem, something strange happened to our collective memory of this environmental triumph. The success story we forgot to celebrate. The cultural amnesia surrounding acid rain reveals something peculiar about human psychology. We have an almost supernatural ability to forget our victories while obsessing over our defeats. Ask anyone about environmental disasters and they'll rattle off Chernobyl, the Exxon Valdez spill, or the garbage patches floating in the Pacific Ocean. But ask them about environmental success stories and you'll get blank stares. Acid rain represents one of the most complete environmental recoveries in modern history, yet it has essentially vanished from public consciousness. The disappearance follows a predictable pattern that psychologists call the solved problem paradox. Once an issue gets resolved, people stop paying attention to it. The absence of crisis becomes invisible, while the presence of crisis demands constant attention. Nobody writes news stories about lakes that aren't dying anymore or forests that have successfully recovered from decades of acid damage. The media cycle rewards disaster coverage because disasters are dramatic, visual, and emotionally compelling. Recovery stories are boring because they represent the absence of problems rather than the presence of exciting developments. This psychological quirk explains why most people think environmental problems are unsolvable. The problems that remain in the news are the ones we haven't figured out how to fix yet. Climate change dominates environmental coverage because it's an ongoing crisis with uncertain outcomes. Plastic pollution gets attention because we're still struggling to address it effectively. Meanwhile, the environmental problems we've actually solved fade into the background like yesterday's weather forecast. The timeline of acid rain coverage illustrates this phenomenon perfectly. From 1980 to 1990, acid rain was everywhere in popular media. Television news programs featured dramatic footage of dead lakes and dying forests. Time magazine ran cover stories about environmental apocalypse. Congressional hearings attracted extensive coverage as politicians debated emission controls and international agreements. The issue had all the elements that make for compelling news coverage. Visible environmental damage, clear villains in the form of polluting industries, scientific controversy, and economic stakes that affected millions of people. By the mid-1990s, acid rain coverage had begun declining even as the policy solutions were proving remarkably successful. The Clean Air Act amendments were working exactly as intended, sulfur dioxide emissions were dropping faster than anyone had predicted, and early signs of ecosystem recovery were becoming apparent. This should have been a moment for celebration and extensive media coverage of environmental victory. Instead, news organizations moved on to other topics. The success story was less interesting than the crisis had been. The media's shift away from acid rain coverage reflected broader changes in how environmental issues compete for public attention. The 1990s brought new environmental concerns that seemed more urgent and dramatic than a problem that was apparently being solved. Climate change was emerging as a major scientific concern. Ozone depletion was generating headlines about skin cancer risks and increased ultraviolet radiation. Deforestation in tropical regions was creating compelling visual stories about disappearing rainforests. Acid rain felt like yesterday's crisis in a world full of new environmental threats. Industry groups that had spent years fighting acid rain regulations contributed to the issue's disappearance from public consciousness, though probably not intentionally. Companies like the Edison Electric Institute had invested heavily in research designed to cast doubt on the scientific consensus about acid rain. When their efforts failed to prevent regulatory action, these same organizations pivoted to compliance with the new rules rather than continuing to publicize an issue they had lost. The absence of industry opposition meant fewer contentious debates, fewer congressional hearings, and fewer opportunities for media coverage. The scientific community also played a role in acid rain's fade from public attention. Researchers who had spent decades studying acid rain moved on to other environmental problems once the policy solutions were implemented and working. Funding agencies shifted their priorities toward emerging environmental challenges rather than continuing to support research on an issue that seemed to be under control. Academic careers are built on studying unsolved problems, not documenting the success of previous solutions. Environmental advocacy groups face similar incentives to move beyond acid rain once the major policy battles were won. Organizations like the Sierra Club and the Natural Resources Defense Council had invested enormous resources in fighting for acid rain controls throughout the 1980s. But by the 1990s, these same groups were turning their attention to newer environmental threats that required immediate political action. Fundraising campaigns focused on emerging crises rather than celebrating past victories. The technology that solved acid rain also worked against maintaining public awareness of the issue. Sulfur scrubbers and catalytic converters operate invisibly, embedded in industrial processes that most people never see or think about. Unlike renewable energy technologies that create visible changes in the landscape, pollution control equipment works behind the scenes. The public never sees the scrubbers removing sulfur dioxide from power plant emissions or the catalytic converters cleaning car exhaust. The technology's invisibility made it easy to forget that the environmental problem it was designed to solve had ever existed. Economic changes in the energy sector accelerated acid rain's disappearance from public consciousness. The shift from coal to natural gas for electricity generation reduced sulfur dioxide emissions even beyond what pollution control regulations required. Market forces were achieving environmental goals that had originally required government intervention. When environmental improvement happens automatically through economic incentives rather than political struggle, it generates less public attention and awareness. The generational change in environmental consciousness also contributed to acid rain's fade from public memory. People who lived through the acid rain crisis of the 1980s remember the fear and urgency that surrounded the issue. But younger generations grew up in a world where acid rain was never a major concern because the solutions were already in place and working. Their environmental consciousness was shaped by different issues: climate change, plastic pollution, species extinction, and habitat destruction. The success of acid rain mitigation created a peculiar form of cultural amnesia where victory became invisible. We achieved something remarkable. We identified a major environmental threat, developed effective solutions, implemented them at scale, and reversed decades of ecological damage. Yet this extraordinary accomplishment has been largely forgotten because success doesn't generate the same emotional response as crisis. The absence of dying lakes and dissolving monuments doesn't grab attention the way their presence once did. This phenomenon reveals something important about how we process environmental information and what conditions actually enable us to solve ecological problems at scale. What acid rain teaches us about climate change. The acid rain experience offers a blueprint for understanding both the potential and the obstacles facing climate change solutions. Both problems share remarkable similarities in their scientific foundations. Researchers identified clear cause and effect relationships between human activities and environmental damage. The atmospheric chemistry is well understood, the measurement techniques are sophisticated, and the predictions have proven accurate. Scientists studying acid rain could point to specific power plants and predict exactly where the resulting environmental damage would occur. Climate scientists can model global temperature changes with similar precision. Yet one problem got solved in a few decades, while the other has dominated environmental discourse for more than 30 years with limited progress. The international cooperation that made acid rain mitigation possible offers both hope and frustration for climate change efforts. The 1979 Convention on Long-Range Transboundary Air Pollution brought together scientists and policymakers in collaborative working groups that fostered trust and shared understanding of the scientific basis for action. This two-way engagement between researchers and government officials created the foundation for effective policy responses. The convention succeeded because it integrated scientific expertise directly into the policy-making process, rather than treating science as an external input to political negotiations. Climate change negotiations have struggled to replicate this model of science policy integration. The Intergovernmental Panel on Climate Change produces comprehensive scientific assessments, but these reports often function more like academic exercises than practical policy guides. The scientific information gets filtered through multiple layers of political interpretation before reaching decision makers. The collaborative working groups that made acid rain cooperation effective have been replaced by formal diplomatic negotiations, where scientific evidence competes with economic and political considerations for attention. The multipollutant approach that proved successful in addressing acid rain through the Gothenburg Protocol provides a template that could be adapted for climate change mitigation. This approach integrated environmental effects with emission source data, atmospheric transport estimates, and abatement cost information to create multiple reduction strategy options focused on effects rather than specific emission limits. The strategy recognized that different pollutants interact in complex ways, and that effective solutions require coordinated action across multiple emission sources and chemical pathways. Climate change involves similar complexity with numerous greenhouse gases and intricate feedback loops between atmospheric, oceanic, and terrestrial systems. The acid rain experience suggests that climate solutions might be more effective if they addressed multiple greenhouse gases simultaneously rather than focusing primarily on carbon dioxide emissions. Methane, nitrous oxide, and fluorinated gases all contribute to climate change, and integrated approaches could achieve greater emission reductions at lower costs than single pollutant strategies. The role of public awareness in driving acid rain solutions reveals both the potential and limitations of science communication for environmental issues. The discovery of acid rain in the 1960s led to extensive research that was effectively communicated to the public, generating the political pressure necessary for legislative action. Scientists studying acid rain developed compelling visual evidence of environmental damage that translated easily into media coverage and public concern. Dead lakes and dying forests provided clear, immediate proof that industrial emissions were causing ecological harm. Climate change presents more challenging communication problems because many of its effects are gradual, probabilistic, and geographically dispersed. Rising sea levels and shifting precipitation patterns lack the immediate visual impact of acid-damaged forests. Temperature changes measured in fractions of a degree don't generate the same emotional response as lakes that can no longer support fish. The complexity of climate science makes it difficult to establish the direct cause-and-effect relationships that made acid rain so compelling to public audiences. The market-based solutions that proved highly effective for acid rain offer important lessons for climate policy design. The cap-and-trade system for sulfur dioxide emissions provided regulated sources with flexibility to select the most cost-effective approaches to reduce emissions while guaranteeing that total pollution would decline. This market-based approach achieved emission reductions that exceeded expectations at costs far lower than traditional command-and-control regulations would have required. Climate change has generated extensive debate about carbon pricing mechanisms, including cap-and-trade systems and carbon taxes. The acid rain experience demonstrates that market-based approaches can work effectively when the policy framework is properly designed and implemented. However, carbon markets have faced political resistance that sulfur dioxide trading never encountered, partly because climate change affects more economic sectors and involves larger financial stakes than acid rain mitigation required. The technological solutions that conquered acid rain were straightforward engineering problems with well-understood chemistry and established manufacturing capabilities. Sulfur scrubbers and catalytic converters could be manufactured by existing industrial companies and installed on existing infrastructure without fundamental changes to energy systems or transportation networks. The pollution control equipment worked by removing harmful compounds from exhaust streams, allowing power plants and automobiles to continue operating essentially unchanged. Climate change mitigation requires more fundamental transformations of energy systems, transportation infrastructure, and industrial processes. The technologies exist to reduce greenhouse gas emissions dramatically, but implementing them requires replacing entire energy systems rather than adding pollution control equipment to existing facilities. Solar panels and wind turbines can generate clean electricity, but they require new transmission systems, energy storage capabilities, and grid management approaches that represent massive infrastructure investments. The industry resistance that delayed acid rain controls initially followed predictable patterns of questioning the science, exaggerating compliance costs, and predicting economic disaster. Coal companies and electric utilities fought emission controls through lobbying, litigation, and funding research designed to cast doubt on the scientific consensus. These tactics delayed policy implementation, but ultimately failed to prevent regulatory action because the scientific evidence was too strong and the environmental damage too visible. Climate change has encountered similar industry opposition, but on a much larger scale and with greater financial resources. Fossil fuel companies have funded climate denial campaigns for decades, using sophisticated public relations strategies to create doubt about scientific consensus. The economic stakes are higher for climate action than they were for acid rain controls, because addressing climate change requires fundamental changes to energy systems rather than adding pollution control equipment to existing infrastructure. The acid rain success story demonstrates that environmental problems can be solved when the conditions are right, but it also reveals why climate change presents more difficult challenges. The scientific understanding, technological capabilities, and policy tools exist to address climate change effectively, but the economic, political, and social barriers are more substantial than those that delayed acid rain solutions. Perhaps most importantly, the acid rain experience shows that even the most complete environmental victories require something that's often overlooked in our celebration of past successes: the fragility of environmental victories. Constant vigilance is the price of environmental progress. We spent decades solving acid rain, but the regulatory framework that made that success possible can be dismantled in a matter of years. The emission controls, monitoring programs, and international agreements that conquered one of our biggest environmental crises exist only as long as politicians decide to keep them in place. And right now, in 2025, some of those protections are under attack in ways that would have seemed unthinkable during the height of the acid rain crisis. The Trump administration's attempts to roll back environmental regulations between 2017 and 2021 provided a preview of how quickly environmental progress can be reversed. The Clean Power Plan, which built on the success of acid rain regulations by addressing carbon dioxide emissions from power plants, was replaced with the much weaker Affordable Clean Energy Rule. Methane emission standards for oil and gas operations were weakened. Vehicle fuel efficiency standards were frozen at levels that ignored decades of technological improvements. These rollbacks didn't target the core acid rain programs directly, but they established a precedent for treating environmental regulations as temporary policies rather than permanent protections. The political pressure to weaken environmental regulations follows predictable patterns that become more intense during economic downturns or periods of political polarization. Industry groups that accepted acid rain controls in the 1990s have spent decades lobbying for regulatory relief, arguing that emission controls impose unnecessary costs on businesses and consumers. These arguments gain traction when unemployment is high, energy prices are rising, or political leaders prioritize short-term economic gains over long-term environmental protection. Coal companies and electric utilities have never stopped fighting the regulations that solved acid rain, even as they've publicly complied with emission requirements. The Edison Electric Institute continues to argue that sulfur dioxide scrubbers and other pollution controls represent regulatory overreach that burdens consumers with higher electricity costs. These same companies fund research designed to minimize the environmental benefits of acid rain controls while exaggerating their economic impacts. The goal isn't necessarily to eliminate existing regulations, but to prevent them from being strengthened or expanded to address other environmental problems. The international agreements that made acid rain mitigation possible face similar pressures from changing political priorities. The Convention on Long-Range Transboundary Air Pollution has been remarkably successful in reducing emissions across Europe and North America, but its effectiveness depends on continued participation by member countries. Political movements that prioritize national sovereignty over international cooperation pose threats to the collaborative frameworks that made acid rain solutions possible. When countries withdraw from international environmental agreements or refuse to implement their requirements, the entire system of coordinated emission reductions becomes vulnerable. Regional variations in environmental enforcement reveal how quickly progress can be reversed when political leadership changes. States that enthusiastically implemented acid rain controls in the 1990s have shown less commitment to maintaining those programs when faced with budget constraints or industry pressure. Monitoring programs that document ecosystem recovery get cut during fiscal crises. Enforcement actions against polluting facilities become less frequent when environmental agencies face staff reductions. The infrastructure of environmental protection requires constant funding and political support to remain effective. The power plant closures that accelerated acid rain recovery in recent years weren't primarily driven by environmental regulations. Market forces, particularly the shift from coal to cheaper natural gas, eliminated many of the worst polluting facilities without government intervention. But these same market forces could reverse if economic conditions change. Natural gas prices could rise, making coal competitive again. Political pressure could lead to subsidies for coal plants in the name of energy security or job creation. The environmental benefits that came from market-driven plant closures could disappear just as quickly if economic incentives shift. Technological backsliding represents another threat to environmental progress that gets less attention than political or economic pressures. The sulfur scrubbers and other pollution control equipment that solved acid rain require ongoing maintenance, upgrades, and replacement to remain effective. Power plants and industrial facilities face constant pressure to reduce operating costs, and pollution control equipment represents an obvious target for deferred maintenance. Environmental regulations require that emission control systems operate properly, but enforcement depends on government agencies having the resources and political support to conduct regular inspections. The knowledge and expertise that made acid rain solutions possible can also erode over time if institutions don't actively maintain their capabilities. The atmospheric scientists who developed the research foundation for acid rain policy are retiring, and universities aren't necessarily training enough new researchers to replace them. Government agencies that implemented acid rain regulations have lost experienced staff through budget cuts and political turnover. Environmental monitoring programs that document ecosystem recovery face constant pressure to reduce costs by eliminating measurement sites or extending time intervals between data collection. The public's short attention span for environmental issues creates political conditions that make regulatory rollbacks easier to implement. Acid rain disappeared from news coverage so completely that most people don't realize the regulations preventing it still exist and require ongoing political support. Politicians can weaken environmental protections without generating significant public opposition, because voters don't remember why those protections were necessary in the first place. The invisibility of environmental success creates opportunities for environmental backsliding. Climate change has absorbed most of the political attention and advocacy resources that environmental groups once devoted to protecting air quality regulations. Organizations that fought for acid rain controls in the 1980s now focus primarily on carbon emissions and renewable energy. This shift in priorities makes sense given the urgency of climate change, but it leaves existing environmental victories vulnerable to attack. The political coalitions that created acid rain solutions have largely disbanded or moved on to other issues. Industry consolidation has created larger, more powerful companies with greater resources to fight environmental regulations than existed during the original acid rain battles. Utility mergers have produced electric companies that operate across multiple states and have significant political influence in Washington. These companies employ sophisticated lobbying operations and can fund extensive legal challenges to environmental regulations. The political balance of power between industry and environmental advocates has shifted in ways that make protecting existing regulations more difficult. Environmental progress isn't a one-way ratchet that automatically advances toward greater protection. It's more like a tug-of-war where constant effort is required to maintain existing gains while working toward new improvements. The regulations that prevent acid rain today could be weakened or eliminated tomorrow if environmental advocates and concerned citizens don't actively defend them. The success story of acid rain mitigation proves that environmental problems can be solved, but it also demonstrates that solutions require ongoing vigilance to survive. This reality forces us to confront some uncomfortable truths about how we remember our environmental achievements and what that means for our ability to tackle future challenges. The acid rain story reveals something profound about human capacity for environmental problem solving. We prove that ecological disasters can be reversed through rigorous science, effective policy, and international cooperation. Yet we collectively forgot this remarkable achievement the moment it succeeded. As Gene Likens, who first discovered acid rain in North America, observed, this is a story where science matters. But our tendency to forget victories while obsessing over failures means we're constantly reinventing solutions we've already discovered. The regulations that keep acid rain at bay still require our attention and protection. Environmental progress isn't permanent unless we actively maintain it.